hold on a second here. Wait a second here. I think you're tricking me. So what I'm working on right now over here is coming from, this one times that one. It's okay. Yeah, there's never a time we end up multiplying this and this in the matrix column multiplication as it happens. Okay, so minus 1/6 e to the t, and then minus 3/7 and plus c2. Of course, it's not surprising that this matches what's right above it. Why? Because these are matching. All right, can we clean this up? We can clean this up a little bit, I think. So what we got is, let's see here. How many? What's a half minus a sixth is a third times a half is a sixth, right? So 1/6 e to the t. And let's see here. Anything else? We got the constants. We got a 3 minus what's 3 plus 3/7? 24/7, which makes 12/7. What isn't what? So I'm pulling off the homogeneous solution. You can see it again. The C1 and C2 are just giving us a linear combination of our fundamental solutions, R1 and R2 we found in the previous example. Yep.
Isn't it 1/3?
1/3. That's true, but then we multiply by a half. Very good. Good question. Let's see here. How about the t's? We have minus 1/2, minus 1/6, which is minus 4/6, which is minus 2/3, which is minus 1/3, since we multiply by half. What's the question, Grace? 12/7. Well, you guys told me that 3 up here, minus 3, 3 plus 3/7 is, I was told 24/7, and then I divided by 2 to get 12/7. But there's a minus that I forgot. That was your question. Very good. In contrast, 3 minus 3/7 is 21 minus 3, which is a bit of 18/7. So 9/7 plus 9/7, I think. And I think that's it, right? So there you go. This is the particular solution, right? If you want to separate it off, and over here, we've got our homogeneous solution that we already knew how to found. Doesn't seem right. We could find the homogeneous solution in our previous lecture. Yep. Uh-oh. Oh, yes. Thank you. They do, but if we redefine, so here. There you go. I'll put tildes on the C's. They're new C's. Let C1 tilde be C1 over 2. Let C2 tilde be C2 over 2. Yeah. But we could absorb the half into the constants for those if we wanted to. What would the scalar solutions be here? So we have x is equal to, 1/6 e to the t minus 12/7 plus apparently c1 tilde e to the minus t plus c2 tilde e to the 7t, and y is minus 1/3 e to the t plus 9/7 plus c1 tilde, minus c1 tilde e to the minus t plus c2 tilde e to the 7t. There you go. Those are the solutions to this non-homogeneous system of differential equations. And so you see that you can solve any non-homogeneous problem. It's just a matter of doing two things, right? What are the two things you have to do? Integrate, multiply matrices. What are the three things you have to do? I will agree with integrate and multiply matrices. Those are, in fact, two of the three things you have to do. What's the other? Keep your signs straight. There are four things that you have to do. What's the fourth thing? It didn't seem like much of an event here because it was a 2x2 matrix. Yeah, we had to find the inverse of a symbolic matrix, right? Because you have to integrate not x inverse of 0, but x inverse of t, or u if you set up the integral with u. So for a 2x2 matrix, yay! Hey, that's a walk in the park. We use the handy-dandy 2x2 inverse formula over here. It's like, yeah, done. What if you had a 3x3 problem? How do you find the inverse of a symbolic 3x3 matrix?
Ooh, I know this.
Yes? MATLAB?
No. You make an augmented matrix with the matrix you want and the identity matrix, and then you do row operations to get the matrix.
Okay. All right. Let's get nuts. So maybe we got like e to the t, e to the t, e to the t. Your other solution is like, I don't know, e to the minus 3t, 0, e to the minus 3t. And the third solution happens to be 6, 7, 8. And then so you're going to take that, and you're going to do row operations on this. You can do row operations until eventually you get to that, right? Whatever's here is x inverse. Sure. You could do that. But you got to be prepared. That means you're going to do row operations that are like time dependent. I mean, that's fine. You can do things like I suppose my initial move would probably be to clear out these two by like subtracting. Well, I guess the first thing would just be row 2 minus row 1, row 3 minus row 1. But at some point, you're going to end up needing to like multiply by functions. You could do it this way. That's fine. I'm not saying it's wrong. I don't really have a good answer to this question for you guys in here. My point is, this is why I would not ask a 3x3 question, because the calculation of the inverse symbolic is above the level of this course. It's really above the level of a test question in any course I teach, because the computation of a symbolic 3x3 inverse it's just kind of beastly. There are formulas that we could use. Actually, I have, in some edition of my notes, I actually have a formula for the inverse of an arbitrary 3x3 matrix. You could use that. There's the formula, this is a formula for inverse. X inverse is equal to 1 over the determinant of x times the classical adjoint, I guess it's called, transpose. So there is a formula for the inverse, but here's the rub. To calculate that classical adjoint, or the adjugate of x, that's a matrix of determinants. So every entry in that matrix is formed by calculating the determinant of the original matrix with that entry's row and column crossed out with an appropriate sign adjoined. So it's sort of a matrix of cofactors. And yeah, that adjugate is precisely this one, D minus B minus CA, right? If you cross out, for example, if you think about A, B, C, D, right? If you cross out the A row and column, what are you left with? D, right? If you, for example, for B, if we take the B and we cross out the B row and column, what are we left with? C, yeah. But you notice that there's a transpose here. Anyway, that's a special case of this more general beast. To derive that, we use Cramer's rule symbolically in linear algebra. So I might even cover this in 221 if I was teaching it, honestly. Okay, so here's where we are. We finished systems. We're about to start the Laplace transform. I actually covered energy methods in a previous lecture, so the course planner is a little bit wrong. I'm just going on. I'm moving on to Laplace transforms. If you guys want to talk about the energy method again, we can do that at some point, but I think it's better for you in the big scheme of the course for us to start Laplace transforms earlier, so you have a little bit more time for them to sink in before the next test, all right? Because certainly Laplace transforms are like a central calculational topic in this course. I think you're going to like them. They're really weird, but it's just algebra. So, thanks guys.